Welcome to the Power Boiler Combustion Control Workshop. In this workshop, you will gain experience working with a typical combustion control system that you would find on a utility or power boiler within the process industry. In the first part of the exercise, we'll examine the combustion control under conditions of increasing demand for energy, and then examine it under decreasing demand, and then look at the impact of the O2 set point on the combustion control. The process that we'll be using in this exercise is a simulation of a power boiler in which the airflow to the boiler is adjusted through a variable speed drive of the forced draft fan. A single fuel is being burned in the boiler. The demand for energy from our plant master is passed through a boiler master, which is an automatic mode of control. So the energy demand is passed on through and goes to our lead lag system. The greater of the two, the fuel or the demand for fuel, is used then in setting the airflow demand, and the fuel that can be supported by the air or the fuel, whichever is smaller, sets the actual fuel demand. The air to fuel ratio is adjusted by PID based upon a measurement of the O2 in the exhaust gas leaving the boiler. Products of combustion are removed through an induced draft fan based upon a pressure measurement using a PID controller. So let's get started with the workshop. In the workshop, the plant master demand is shown at the very top. It is coming as an input to our boiler master, which is a bias gain station in automatic mode. The output of the boiler master then is used to set the through the lead lag system, is used to set the airflow to the boiler, and also based upon the demand through the lead lag system, we establish the fuel demand for a boiler for safe combustion within the boiler, and also while meeting the requirement of the energy demand. In the exercise, the plant master demand is constantly changing, so we can examine this under varying conditions. So let's look at a chart to better visualize the response to the combustion control as there's changes in energy demand. As we see here, under decreasing energy demand, the fuel flow lags the demand in terms of reduction, but the air, since it's based upon the greater of the two, is the correct amount. On increases, the demand for energy sets the air, so there's always sufficient air to burn the fuel. And so under all conditions then, safe combustion is maintained in our boiler through the lead lag network that makes up the combustion control system. To examine the impact of the O2 set point on the combustion control, we'll change the O2 set point from 2% to 3%. For a 1% change in O2, this will require about a 5% change in total air requirement. The O2 controller adjusts the air to fuel ratio to achieve its target O2. The impact of this can be seen by looking at our chart. As we see here, when we increased the O2 set point, the airflow was immediately increased, and as the energy demand picks up, we see that for the same energy demand that we had before previously on an increase, we now see a greater amount of air, about 5% more air being used in the combustion process, and as a result we notice that the O2 is now running at 3% rather than 2%. So through the O2 control and its adjustment of the air-fuel ratio, we're able to precisely maintain the O2 required for efficient combustion in the boiler. We hope that this exercise has been helpful to you in understanding the lead lag system that's provided on a power boiler in the process industry. We would hope that you use this exercise to further explore combustion control